So let us look at this particular circuit and let's see how we can implement this thing, right. So if you have n bit numbers and you want to add two n bit numbers, right, two n bit numbers, addition results in n plus 1 bit number. Okay, this is the fundamental thing. So the sum will be n plus 1 bits always. Okay. So now let us look at just two examples of what happens if I were to treat this system as two n bit numbers, right, which is a and b. That means I have two n inputs, right. So you just go back here, this adder here that we were talking about, we are talking of 16 bit input and 9 outputs. Okay, A0 to A7, B0 to B7, S0 to S8. Okay, we are talking of 9 outputs. Similarly, if I just look at a simple 4-bit case, A, B, sum, this is going to be 5-bit answer. Okay, so I can simply treat this as A3, A2, A1, A0, B3, B2, B1, B0, and then 5 outputs, S4, S3, S2, S1, S0, right. So now what you can do is technically you can look at this as an 8-bit input, A and B, and simply go through all 2 power 8 combinations, right. And then you know that, for example, 0 plus 0 should be all zeros. Okay, I am just considering the unsigned number for now. Okay, unsigned number. Okay, then 0, 0, 0, 0, 0, 0, 0, 1, answer should be simply this, right, and so on. You just keep doing this whole thing, you populate the entire truth table for 256 combinations, 2 power 8 combinations, and you can actually do, you know, the Boolean simplification for each sum and all that stuff and get the answer, this thing. Okay, now obviously this thing is not going to scale, because the moment I just look at, for example, from 4-bit to 8-bit, if A and B were 8-bit, I am talking of 16 inputs, I am talking of 2 power 16 with combinations, right. Clearly this is not going to work, it is going to go out of hand. That is one thing. Second, these S0, for example, is going to be written in terms of A3, A2, A1, A0, B3, B2, B1 and B0, right. But invariably that may not be the best possible implementation, and therefore in some circuits like the adder and, you know, the other circuits that we will discuss in this later this week, we can exploit a certain structure in this addition circuit and then break this down into a 1-bit adder or whatever, right, and then use that to build hierarchically the n-bit multi-bit adders, right. So that is what we are going to do. And if we go back and look at this, you know, whole carry the carry propagation through the addition circuit, all we, you know, you look at a single bit position here, right. It basically is going to take 3 inputs, a, you know, bit position, you know, bits AK, BK of the inputs A and B, okay, of the kth position bits, and a carry that is coming in from the previous circuit, right. That's all I need to do, and the output of that circuit will be 2 things. One, it will generate its sum bit and then propagate a carry to the next stage. Okay, So this is what we have, and therefore I can now, by the way, I'll just call this the adder, right. So I can now define what is known as a full adder. Okay, it simply takes, for convenience, I will draw bits A, B, okay, C in, sum, C out. Okay, this is what we have, and we are going to go ahead and see if we can use this in order to build the n-bit adder that we want. Okay, so now we are in comfortable space because we have only 3 inputs and we have 2 outputs. So we have A, B and C in. Then you have sum and C out as the outputs. Now I can enumerate all possible combinations. 1 1 0 1 1 1, right. This basically is all possible combinations, and now you just look at the sum. Okay, if you add 0 plus 0 plus 0, obviously the sum will be 0, carry out will be 0. If you add 0 plus 0 plus 1, there is no problem, sum will be 1, carry out will be 0. So both, this is what will happen. When you reach 2 ones of the 3 inputs A, B and C in, your sum will become 0 because 1 plus 1 is 2 and therefore the sum bit is 0, carry out becomes 1. Okay, so this will be 0, 1. Okay, and then we are talking about the next 4 cases, right. Again 1 0 0, if you add, you are back to 1 0. Now you are adding 2 ones, so therefore sum is 0 but carry is 1. This is 0, this is 1, and the last case 1 1 1, talking about the sum and carry out being 1 each. Okay, now you can therefore go ahead and build your K map as usual for this. Right, so this is 8 inputs, so I have this, right, and B, C in A, 0 1 3 2 4 5 7 6, B bar, C in bar, B bar, C in, B C, C in bar, sorry, not bar, C in, A bar and A. Okay, so I have this, I can make a copy of this, right. Yeah, one of this I will use to evaluate the sum and the other I will use for the carry, right. The sum is just min terms. Okay, so if I write this summation min terms 1 2 4 7 4 7, C out is summation min terms 4 0 1 0 1 2 3 3, sorry, 3 4 5 6 7. Okay, so I have this and therefore the sum is going to be 1 2 4 7, 1 2 4 7, right. And this is, there is not much of a pattern here or a Boolean simplification that you can do. Likewise, let's look at what it is for C out 3, 5, 6, 7, right? So you have 3, 5, 6, 7. At least here there is something. So let's start with C out. Okay. So I can do this Boolean, right? So it is, if you look at this, this will simply be AB plus AB plus B C in plus A into C in. Okay, there are 3 different terms that will come out of this. The sum is obviously going to be more complicated. It's just sum of 4 different things. So you just write this as A B bar C in bar, okay, plus A bar B bar C in plus B C in plus, sorry, B C in into A B C in plus A bar B C in bar. Okay, so I'll just rewrite this a little bit and I'll show you that this can be written as, okay, I'll group these 2 terms and I'll group these 2 terms. I can write it as A into B bar C in bar plus B C in plus A bar into B C in bar plus B bar C in. Okay. Now this I can simplify further as, this is B XOR C in whole bar plus A bar into B XOR C in, right? And you can therefore write this as A XOR B XOR C in. Okay. So this is a very nice representation using the XOR operation that we got. Okay. So let us maybe just look at, implementing this particular circuit with the following standard cells. Okay. I have XOR gate, XOR 2. Okay, and then I have AND 2, okay, and I have let me just say AND 3 also, just in case. Or 2 or 3. Okay, so this is what I have, AND 2 and 3 or 2 or 3. So suppose I had this as my standard cell library, right? Then it is quite a trivial implementation for us to get the sum and carry. So I have A, B, C in, okay, and my carry out is simply this pairwise A, B, B, C, C, A. Okay, so I will say this is B and C, can be in any order by the way. This can be A and B, and this can be A and C, right? And then finally I simply do an OR operation here, right? Right, and this is my C out. Okay, now if I have the XOR gate available as shown in my standard cell library, then it is possible to do this like this. Get A XOR B out here, and then you generate sum. Okay, this is my sum bit, this is my carry bit, and effectively this is the Boolean implementation of the full adder. Okay, there's something called a half adder where basically the carry in can be assumed to be 0, right, in which case the sum will just become A XOR B, okay, and C out is just going to be A into B, that's all, A and B, right. So those two other AND gates will go, the OR gate will go, and you will just get C out equal to A and B, that's it. Okay, now using this particular adder or a full adder that we built, we can go ahead and do what is known as the n bit ripple adder. Okay, so the ripple adder is like this. Okay, I have full adder 0. Okay, the carry in for this guy is grounded because we don't consider a carry in when we said A plus B, right. 0th bit position never had a carry in, right. So then I would simply feed A0 B0 into this B0, FA1 will get A1 B1, the sum is going to be S0, this is going to be S1, okay, all the way you just keep doing this. Okay, so the carry out of FA0 is being fed as carry in to FA1, okay, and then you come to the last adder. Okay, this is FA n minus 1 because it's an n bit adder, A n minus 1 B n minus 1, the carry is coming from the n minus 2 adder position there, and this will give you S n minus 1, right. So if you go back to the example that we did for the full adder, the n plus 1th bit of the sum always came as the carry out of the last stage. So if you look at this, the you would add in bit position 7, you add 1 plus 1 plus 1, that 1 comes up, okay, and that appears here because you have sign extended this, right, and you will get the answer here. Okay, so now for now we are talking about the unsigned adder. Okay, so you do this and then the carry out is going to come out as Sn. Okay, so with that you basically will get a ripple adder for unsigned numbers. Okay, this you must be careful. This is for unsigned numbers. Okay, now if I were to now treat A and B as signed numbers, then I need to do something slightly differently here. Okay, I still will need that n plus 1 bit Sn to come out. Okay, but that is not so trivial. It is not the carry out. For example, if you go back and see this addition here, right, what we got 1 plus 1 plus 1, it just so happens that it's so it's something that you have to be a little careful about. Oh no, I think for signed numbers also this essentially will be the case, right, because the carry out is going to be the final bit there, right, because let's see, suppose it were 0, 1 0, yes, correct, okay. So this is unsigned numbers and signed numbers. Of course, this is 2's complement. Okay. So, what is the difference between this implementation and the initial implementation that I said was going to become intractable, right? This truth table enumeration, right? What this was assuming is that all the inputs, right, A3 to A0, B3 to B0 are all going to control S0, right? Everything will control S1, right? That is first of all not true, right? And in some cases it's not true, in some cases it is true. For example, S0 is not determined by B1, A1, B2, A2, the higher bits at all. It is determined entirely by A0, B0. However, S1, the sum 1 bit is indeed determined by A0 and B0 because that depends on the carry, right? Like this you can keep going, the highest bit Sn minus 1 will depend indeed on all possible bits that are there before it, right? So that's why this is actually a very complicated implementation to get, directly, okay? But what we have done here is, we are saying you evaluate for A0, B0 and then propagate that carry through in a step-by-step fashion. So if you look at Sn minus 1, it is indeed dependent on A n minus 2, B n minus 2, A n minus 3, B n minus 3 all the way to A0, B0, but it actually takes only the carry in of the n minus 2th stage, right? Bit n minus 2, not n minus 2th stage, bit n minus 2, right? And therefore, Sn minus 1 depends on C out of n minus 2, right? However, C out of n minus 2 in turn depends on all these bits, right? So that is why this is basically a nice hierarchical design which is just using a full adder as your base unit and then propagating signals. We are taking the output of one stage and giving it to the next stage and so on, okay?